Okay, hi guys. We're going to talk again about endothermic reactions. We're going to do it in a little bit more detail. Hopefully you should be familiar with the term endothermic. As we went through it last time, the endo means enter, okay, and thermic means heat. So it's a reaction that heat goes into the chemicals. Now, this was a thing that confuses people quite a lot, because actually when you think about it, it's not that intuitive. If, for example, I have a cold pack here, Mr. Freeze, okay, and I pop the bag inside, the chemicals mix and it gets colder. I will have a temperature drop, so say it starts at 20 degrees C, about room temperature. It will drop down to around about 5 degrees C. Okay, which obviously is a drop of 15 degrees C. We can tell that that's an endothermic reaction because we've lost 15 degrees of heat. But actually, what are we measuring here? That's really the key thing. What we're measuring is actually the surroundings. The chemicals themselves are gaining energy, but they're gaining it from the water or the solution that they are in. If we were to zoom in here, okay, which I'll do nice and big, okay, and I'll draw my chemicals just as the letter C, just to make it easier. It's not carbon, it's just the letter C, right? These are my chemicals. I've also got, now surrounding those chemicals there is water, okay, H2O. Now you should remember from physics that actually, you know, that water's got energy. Water stores energy, and we can measure how much energy is stored in the water. Okay, one of those measures is by taking its temperature. Okay, so there's my thermometer. Gosh, it's not a great thermometer. Okay, so I can take the temperature of the water. Okay, and that tells me roughly, or it tells me it's a loose guide as to how much energy it's got in it. If the temperature's high, it's got a lot of energy in it. If the temperature's low, it's got less energy in. But what happens is, when these chemicals start to react, they need to take energy in for the reaction from the water. Okay, so the water is giving them the energy. So what happens to the temperature of the water? The temperature of the water is going to drop because it's losing energy. Okay, and the energy is going inside these chemicals. We cannot measure inside the chemicals, which is why it's difficult, which is why this doesn't quite seem as logical as it should do. But if you understand that what you're taking the temperature of is actually the surroundings, it's not the actual chemicals themselves, then you should be okay with this, right? So if we've got a temperature drop, if we can measure a temperature drop, it's endothermic. But counterintuitively, the chemicals are actually gaining energy, and it's the surroundings that are losing energy. Okay? We can show this in another way. So we can show this in another way, as I just said, by using something called an energy profile diagram. Okay, and this is essentially like a graph, but not quite the same. Up my y-axis, I will have energy. And on my x-axis, I'm going to have time, okay, or progress of reaction. Okay, and that is going to show you basically what happens to the energy over time. Now, to start with, if I've got an endothermic reaction, my reactants might be quite low in energy. Okay, so they're down here. Their products will be higher in energy. Okay, and you can see that there's obviously going to be a difference in energy. So as the reaction goes ahead, we get a line going up, it goes up higher and then drops back down to the products. Okay, I'll explain what that top bit is in a moment. Okay, but you should see this difference here is energy required. Okay, it's going to be the energy taken in by the chemicals from the surroundings. Okay, and this bit at the top here, between here and here, that bit there is called the activation energy. Okay, and that it's the amount of energy needed to activate or to start the reaction. Okay, I'm just going to try and move that a little bit so you can see it says progress of reaction. Okay, so yeah, it says activation energy. So it's the amount of energy needed to start the reaction. Okay, energy needed to start reaction. Okay, and that will vary from reaction to reaction. The amount of energy required is going to vary from reaction to reaction. But if you've got the reactants low in energy and the products high in energy, it's going to be an endothermic reaction. Okay, and this energy comes from the surroundings. Okay, and that could be air molecules, it could be the air around it, it could be the liquid that the chemicals are dissolved in. Okay, it doesn't matter, but if you measure a temperature drop, then that means that there is energy required to get from the reactants to the products. Okay, it's also the case when we had our heating up of our carbonates, okay, with thermal decomposition, which we talked about last time, which looked like this, do you remember? Okay, because there's heat energy going into those compounds. Again, the reactants are lower in energy than the products, right? And that is what you need to know for endothermic reactions. Okay, I hope that was all right. If you've got any questions, let me know. Stay safe and complete the worksheet. Cheers.